Hello again, everyone. Welcome back to our course in trigonometry. I wanted to tackle some applied problems in this video. Applied problems that involve linear and angular velocity. And the real reason I'm using the document camera is I want to do this. So let me grab a problem from the textbook for our course. So let's go down here. Okay, so we're looking right here at problem 51. Zoom in right there like such. Okay, so the problem tells us that a ski lift operates by driving a wire rope from which chairs are suspended. We got this little figure right here. So this big wheel is going to be turning, and this wire rope is attached to the wheel. It's kind of stretched over the wheel, so as the wheel turns, the wire rope moves with it, and the cars that are attached to the wire rope then move along the lift. So they're telling us that this big wheel is 12 feet in diameter and turns at a rate of 9 revolutions per minute. And they're asking us, what is the linear velocity of someone riding the lift? So we can figure out the angular velocity of the wheel, and then once we've got that, figure out the linear velocity of a point on the edge of the wheel, which will tell us how fast the rope is moving, which will tell us how fast someone riding the lift is moving. Okay, so let's start to kind of work some of that out. Let me ditch the book for a sec and zoom back out so we can see what we need to see here. Okay, so in this example, we're working on that ski lift problem. Now, the diameter of that big wheel was 12 feet. So the radius of that wheel is 6 feet. Now that's going to be important. They also tell us in the problem that the wheel makes 9 revolutions per minute. Now we need to convert that to angular velocity, so radians per minute. Well, every complete revolution is 2 pi radians. It's making 9 revolutions per minute, so 9 times 2 pi. Okay, so the angular velocity of that wheel is 18 pi. Now, if you remember from our last video, we figured out a relationship between linear velocity and angular velocity. Okay, and it was r times omega. That's how we found linear velocity. So, we know the radius of the wheel is 12, the diameter is 12 feet, so the radius is 6 feet. And we know the angular velocity is 18 pi radians per minute. So we'll take 6 times 18 pi, and this is going to end up being feet per minute. Radians are really like dimensionless. To find radians, you take the intercepted arc, which is in whatever linear unit you're using to measure, and divide by the radius, which is in the same units. So radians don't really have units. Okay, so let's see here. 6 times 18, so that's 60, so that's 108 pi feet per minute. Now let me go back and look at that problem again. They did ask me to find the linear velocity in feet per second. So now that I've got the linear velocity in feet per minute, I'm going to convert to feet per second. Okay, so I'm thinking about the units I have. Feet per minute. Now, of course, I know 60 seconds is 1 minute. But I got to think about how I should present my conversion factor. And I think I need to do it like this. Now, the reason that I think I need to do it like this is because I want my answer to be in terms of feet per second. So I want to cancel out the minutes. So I should put the minutes in the numerator to cancel out the minutes down here in the denominator. And if I got minutes in the numerator, that means I should have seconds down here. So 1 minute, 60 seconds. So I should set up the conversion factor this way. Let me see here. Well, 108 is divisible by 6. We just saw that, so that's a 10. An 18. So 18 pi over 10. And then, of course, we can cancel even more. So 9 pi over 5 feet per second. And if we were so inclined, we could use our calculator to calculate. 9 times pi. My calculator even has a, whoops. I guess it would help if I turn the calculator on, right? So 9 times pi, divide by 5. So we're talking about 5.7 feet per second. So that's the speed of someone riding that chairlift. And if you think about it, that makes sense. You might say, well, 5 feet per second, that's kind of slow. Well, the chairlift needs to go kind of slow. You're not really strapped into those things, right? So you can't be going 100 miles an hour. Okay, let's look at a second problem. A second applied problem. Okay. This picture is kind of important for the problem that we're going to work on here. So we're going to imagine that this lighthouse is 100 feet from a long straight wall on the beach. Okay, so they have that right here. That's the distance measured from the lighthouse's light to the wall. It's 100 feet away. Now, of course, we've all seen, we've all seen movies and things like that. So the lighthouse has this beacon of light, and it rotates. And in this problem, they tell us that the light rotates through one complete revolution every 4 seconds. Okay, so it takes 4 seconds to do a full turn. And what they're asking us is, we want to find an equation that gives this distance d in terms of t, time t. All right, so here's how we're going to tackle this problem. We're going to need to let's do a top-down view here. So there's the wall. This is the lighthouse, light. The hypotenuse represents the beam of light coming out of the lighthouse. We were told in the problem this is 100 feet. We want to know this. So let's imagine at time t equals 0, the light is pointed at the wall, okay? And as the lighthouse rotates, the beam of light will be pointing at different places on the wall until it turns around, okay? So, we're going to use some trig functions here. So we're going to think about this angle theta, okay, in terms of t. Okay, so the time that it takes to do a complete revolution is 4 seconds. So, I'm thinking that we need this here. Theta equals t over 4. Okay, and let me just kind of walk you through my thought process for doing this here, where t is in seconds. Okay, let's pretend we wait 8 seconds. Okay, if we wait 8 seconds, then the lighthouse would spin 2, so that's 4 seconds there, and that'd be 8 seconds, 2 complete revolutions in 8 seconds. And if I put in t equals 8 here, I get 8 over 4. Okay, so now I guess I do need to kind of scale this, because I really want theta to be an angle, so I should probably multiply that by 2 pi. Okay, so that is the angle that we've gone through. So every 1 second, you go through an angle of pi over 4 radians. Oops, sorry, the two would cancel right there. So it'd be pi times t over 2. So that's my angle theta. Now, let's look at the relationship between theta and d. Okay, we got some trig functions here. D is the opposite side. D is the side opposite angle theta, and this is 100 feet here, so that's the adjacent side. So I know that tan theta would be, well, tan theta is opposite over adjacent, d over 100. So that would mean that d equals 100 tan theta, and we also were expressing theta in terms of t. So I think this works as an expression for d in terms of t. So it tells us the distance along the wall that the light is shining given the time t. Now, a couple of things to note here. Okay, when t equals 2, I have tangent of pi in my expression. Okay, so let me figure out what that is. Tangent pi. Oh, okay, that's fine. Oh. Yeah, okay. Actually, it's when t equals 1, I'm kind of in trouble. Oh, yeah, t equals 1, I'd have tangent pi over 2. Let me look at that. Tangent pi over 2. Yeah, that's a problem, right? Oh, you know what? I'm in degree mode. I was wondering why this is giving me funny answers. Okay, so I want to change my calculator to radian mode. Okay, now tangent pi over 2. Now I can see why I've got a problem. Okay, tangent pi over 2 is undefined. Well, so let's think about what's happening here, right? So At time t equals 0, the light is pointed right there at the wall. And 4 seconds to do a complete revolution. So 1, 2, 3, 4. Okay? So at 1 second, the light has moved pi over 2 radians, or 90 degrees. So the light is actually parallel to the wall. So it actually does make sense that when t equals 1, this expression is undefined, because the light isn't pointed at the wall at that time. Okay, so it's a neat little problem there, relating angular velocity and the trig functions that we've been discussing in our course.